Hello and welcome to Science Talk. I am your host, Jim Massa. In this continuation of bringing to you some news involving climate change, I left off the last video discussing extinction rates. On this one update here, discuss marine extinction risk. Okay. Professor Daniel Rothman is a geophysicist at MIT, Massachusetts Institute of Technology. He reports in the journal Science Advances that the risk to marine life forms is greatly increasing due to warming temperatures. Now, you may have heard, may be familiar with the issue of coral bleaching. What's basically happening there is the increased temperature of the water around the tropical reefs, specifically here, is causing the corals to die. Within the corals themselves are little polyps. These are the actual organisms. They secrete the calcium carbonate that helps build the reefs and so on. But within the polyps themselves is a symbiotic algae, basically, symbiotic autotrophic organism. The autotrophic organism is offered protection within the polyp because the polyp can withdraw itself inside its calyx. It photosynthesizes it. Some of the products of the photosynthesis is given to the polyp in case the polyp is unable to procure enough food from its feeding tentacles. Well, the increased temperature is causing these, what they call zooxanthellae algae, to die, which then causes the polyps themselves to die, leaving the white corals behind. That's a problem there. Also, the increase in temperature, not only from the CO2, but the CO2 reacts with the water to form carbonic acid, H2CO3. Carbonic acid then lowers the pH. Many organisms, from limpets to various mollusks and so on, their shells are made of calcium carbonate. The shells are starting to dissolve due to the increased acidity, putting these organisms at risk. And they're now vulnerable. Their physiology is compromised. They're vulnerable to predation and so on. What is important also to remember is, and I'll be discussing this in a later video, is the specific heat. Water has a much higher specific heat than the air. Specific heat is basically how much energy is required to raise 1 gram of an object 1 degree Celsius. Okay? That's what a specific heat is. In the old days, used to measure as calories, kilocalories, and so on. We prefer nowadays to use joules as the unit to measure this by. Water has a much higher specific heat. So in order to raise a body of water 1 degree Celsius and a same corresponding volume of air 1 degree Celsius, to raise that volume of water, that 1 degree Celsius, requires much, much more input of energy. So we have all this extra heat coming in. A lot of it is being absorbed by the ocean. And this is what sort of saved our bacon for the moment. Not really, if you think about it. But it will come back to haunt us in the future. So what Professor Rothman is finding, along with other researchers from the University of Washington, Seattle, senior author Julian Alden, is that this is affecting also fish. Because warmer temperatures, fish have to migrate. They need to get to whatever temperature range they prefer. Many people planet-wide rely on fish for their food. This poses obvious threats. What about those are fish in the ocean? What about fish in lakes? They can't really go anywhere. This puts them at high risk. What if you have indigenous people in a landlocked environment, not within coastline, and there's a local lake that they fish out of, and those fish start dying off? What happens? So that is another issue. We're seeing increased extinction rates of aquatic life forms, not only in the marine environment, but in the freshwater system as well. A warmer world will impact agriculture. Okay? A researcher, Dr. Denier, who is an environmental engineer at MIT also reports in the journal Science Advances that unless serious reductions in global emissions of CO2 and other greenhouse gases that are driving global warming and could trigger catastrophic climate change, the most extreme once in 25-year heat waves could increase wet bulb temperatures now at around 31C to 34.2C. At 35C, few humans could survive more than a few hours. In my earlier video, I discussed this. Well, he is doing some more research that basically lends support to this finding. But what is the real critical, what he did here was he looked at agricultural production. As you increase heat, agriculture suffers. Many plants that most humans use for crops and agriculture, most of those plants prefer a temperature range about 20 to 25, maybe 28 degrees C. And these are wheat and soybeans and other grasses and so on, rye, etc. Higher temperatures, these plants do poorly. They die. Part of the reason they die is their metabolism. Many of these plants are what we call a C3 plant. What is a C3 plant? There are two types of metabolic pathways plants take. C3 or C4. Basically, the C3, C4 simply refer to an intermediary product in the long series of chemical reactions that ultimately result in glucose. In the C3 plants, an intermediary product has a chemical with 3 carbon atoms in it. The C4 plant, a product that has 4 carbon atoms in it. But the methods of which they get here vary greatly and are a function of temperature. In hot environments is where you'll find C4 plants. And it's related to what the stomata, the openings on their leaves do, and how they open, how much CO2 they let in, and so on. The only C4 plant that is important to, as far as human use, is corn. Okay, corn is really kind of the exception. C3 plants, in essence, the short of this is, C3 plants do not handle high temperatures well. C4 plants thrive in hot areas and low humidity. But again, C4 plants are typically not food plants. Hotter temperatures do not bode well for C3 plants, which is our food plants. And it may surprise you that as you get hotter and hotter, yes, we know that the warmer the air is, the more moisture it can hold, up to a point. And at about 103 degrees Fahrenheit, the air becomes dry. The air is not able to hold moisture. And that's where the C4 plants thrive in. They thrive in hot temperatures, low humidities. C3 plants, that's C4 plants. C3 plants do best in a range of about, say, 50 degrees Fahrenheit up to about 85 degrees Fahrenheit. Lower temperatures, higher humidities. Continuing on. Climate warms the earth. Not chance. Okay? Basically, what this is stating is that the warm temperatures is not due to just random events, but simply due to human activity. Okay? Michael Mann. He is one of our leading climate scientists. He is found working at Penn State University. You may remember him from, if any of you watched Al Gore's Inconvenient Truth, he was a featured scientist in that movie, and he was the one that drew what is now known as the hockey stick graph, where we see, levels of the temperature, and then bang, makes a sharp uptick like you would find on a hockey stick. As I mentioned earlier, there's a direct correlation between CO2 levels and temperature. Increased CO2 levels, temperature increases as well. And what he's basically did was he examined the temperature record for the last decade or so, and he calculated the chance that 13 of the warmest 15 years ever, occurring all in the first 15 years of this century. In other words, he went back a couple of decades, and there's been 13 very, very warm years. 13 of those very, very warm years have been in the 21st century. And he basically said the probabilities that this is due to chance is at its lowest 1 in 170,000. In other words, the short of it is humans are creating changes to the climate. Other studies have demonstrated that humans account for about 73% of the variation in observed climate change. In other words, we are having a greater impact on temperature and climate changes than that can be simply explained by natural cycles. Because the climate deniers have argued that this is just, natural variations in Earth's climate. Yes, the Earth has changed before in the past. It has gone through warm spells and cold spells and so on, recurring ice ages. But what people fail to understand or comprehend is it is the rate of change. Changing so rapidly nowadays. That is the key difference. It's the rate of change. If we would take a derivative, and throw a little calculus in here, if we were to take a derivative, we would find that the rate of change is greater now in the 21st century than it was in the 6th century. Or 35,000 years ago. It's the rate of change. That is the key difference here. That is the key point as to what's going on with the climate. And if you really wanted to, some of you may or may not be familiar with the scientist named by Milankovitch. He was a Russian scientist who was doing his research during World War II, and he wanted to find out why does the Earth go through ice ages that appear to come in cycles. And basically what he discovered and came to conclude was that there were changes in Earth's orbit, the shape of it, what's called how eccentric it is, how elliptical the Earth's orbit is, the shape of it. The tilt of the axis, the Earth will tilt from varying from like 23.5 degrees to 24, 25.5 degrees, thereabouts. As well as precession of what's called the equinoxes and the solstices. Variations in these three major factors lead to how heat is distributed over the planet, and thus affecting incoming heat distribution can trigger ice ages and trigger interglacial periods. So if we were to look at Milankovitch right now, Earth should actually be entering into a cooling stage. But we're not. We're warming. So imagine if Milankovitch predicted that we would be entering into a warming stage, we would really be exacerbating the situation, as it would be a lot worse. Now, Milankovitch is not perfect. His variation explains about 70%. So what's the other 30%? That is still being researched and trying to come up with that. But it's like anything else. When you create a model, regression model, linear, curvilinear, what have you, any complicated computer model, one of the things we look at for a defined independent variable is we want to see, okay, how much does this independent variable, how much of the variation does said independent variable explain of the response? Now typically, with good models, we want at least a minimum 85% variation explained. Sometimes it could be that two variables will explain 97% of the variation. That's a good model. You have two variables that explain most of the responses seen. So obviously 70% is a good start, but it's not the sole factor. So other factors need to be considered. But I digress. Okay. The next topic I wish to share with you is one that you see climate deniers always trotting out saying, oh, it's all global warming is all made up hooey and this, that, and the other thing. And of course, you had that illustrious senator, the illustrious Mr. James Inhofe of Oklahoma, bringing a snowball onto the Senate floor and saying, see, there's snow outside, global warming is a joke. Well, Mr. Inhofe, warmer airs hold more moisture, so when you have a lot of snow falling on the ground, that's because there's more moisture in the air, which means it's warmer. It comes as snow because, hey, we're still tilted away from the sun. I just love it when scientists, when politicians who don't know anything about science try to tell us what's going on. And they're the ones that make policy. This is what's scary. Okay? They bring in scientists to testify, give their expertise to Congress, and then they proceed to lambast them, telling them you're an idiot, this, that, and the other thing. For example, a politician will ask a scientist, can you say with 100% certainty? No. Any scientist worth his or her salt will never ever say, I'm 100% sure on something. They always say, well, I can state with 95% confidence or 95% probability. This is technically 0.95 probability, right? But they'll say that. They'll never say, oh, I'm 100% certain. Any scientist that says that is not a scientist, not a good scientist. But when a politician hears that, they just want to hear 100% certainty. So a scientist will say, well, I can say with 95% certainty. What about the other 5%? Well, that's variation. So you don't know. And this is when the scientists will probably throw their hands up and say, what the hell? But it's that kind of mindset that is really detrimental. Why do I mention that? Because I'm going to talk to you about the so-called global warming hiatus. Okay? There was a period in the mid-00s where global warming did not seem to be occurring. It seemed to be a hiatus. Temperatures remained the same. They weren't getting any warmer. Might have been cooling down and so on. Well, Professor Stephen Belcher, who is a chief scientist at the UK Met Office, basically, they call it data from the Met, shows that the rate of global warming has now returned to the level seen in the second half of the 20th century. What came into play was, you heard me mention ENSO, El Nino Southern Oscillation. There's also tied into ENSO is another phenomenon called the Pacific Decadal Oscillation, or the PDO. These working in conjunction can create cooler than usual conditions than from the long-term average. So the fact that there was no warming but maintained the same level was probably due to the PDO being in play, and that PDO is now moving out of its cycle into a warmer phase. And by the way, I should also mention there is the North Atlantic Oscillation, the NAO on the North Atlantic side as well, that can affect local climate. So basically, as I said here, this is a quote from Professor Belcher. The so-called hiatus in global warming between 1999 and 2014 was a phenomenon much hailed by climate denialists as evidence that global warming did not exist or had stopped. Okay, so why was this going on? Well, the world was still warming steadily, but as it turns out, and that leads me into the next article, is the role of the oceans. And the role of the ocean explained why there was an apparent hiatus in the climate. Basically, the short of it is the ocean absorbed the heat. So it didn't necessarily stay in the atmosphere, it was absorbed by the ocean. And as I said before, the Pacific heat of water is much, much higher than air, so a lot more of that energy is being absorbed by the ocean. And why did the ocean absorb more? Changes in atmospheric circulation as a result of messing with the planetary-wide system. The ocean and atmosphere are a coupled system. For many years, atmospheric scientists did their thing, oceanographers did their thing, and at some point basically said, hey, maybe we should work together. Brilliant idea. And there's a lot of stuff that goes on at the ocean-water interface. So, in essence, the oceans absorbed more of the heat, and that's why it gave the apparent appearance of climate change, global warming not proceeding, getting any worse. Well, as we now know, looking at the data from 2014, 2015, 2016, 2017, these are the 3 hottest years. We keep breaking records every year. So, that's the short of that. The other thing that goes on is as the planet warms, ocean levels are rising. We're now measuring that. But the ocean level rises from 2 main factors. One is the addition of land glacier. Greenland, Antarctica are the major contributors. Smaller contributors being alpine glaciers. Sea ice is sea ice. I mean, seawater freezes, it melts. It's the same. That's not going to affect the volume. That's the same thing. If I take, a glass of water and I freeze it and then I melt it, it's the same volume. But if I take a glass of water and then I add an ice cube to it, well, that's now, and that melts, that will raise the level of the water in the glass. So sea levels are increasing, rising due to melting of land-based glaciers, but also thermal expansion itself. You heat up an object, it expands. So you have a twofold thing. Adding water from melting glaciers, heating the water itself, and thereby expanding. Well, when you expand it, it can create more storms, but it can also increase the surface area to increase the absorption of more heat energy. And what does that then do? Ocean warmth will predict increased drought and fire risk in the U.S. Okay? And we're seeing that already. Look what's going on in California. All the forest fires in December, November. What gives? And basically, scientists from Utah, South Korea, Hawaii, the UK, and California report in the journal Science Reports that they were able to show that without anthropogenic effects, the droughts in the southwestern U.S. would have been less severe. Axel Timmerman was the lead scientist on this study, and he was the one that reports this. In some of his reporting, he basically says if the Atlantic is warm while the Pacific is relatively cold, the risk of prolonged drought and wildfire conditions in California and on the other side of the Rockies becomes higher. It is a natural consequence of oceanic cycles, but these scientists warn that global warming can also make these droughts more severe. The implication is that sustained drought followed by raging wildfires will do what? It will leave barren areas. Now there's dead plants there, nothing to hold the soil. So should rain events do happen, you have increased erosional runoff. You lose your topsoil. You lose your ability to plant plants for agriculture. So this has severe consequences. Now, of course, no single climate event can be contributed to just climate change or what have you. You can't just say, oh, this one event is climate change in action. But when you take a series of events, then the indication is that yes, this is a result of human activity. I'll give you an example. Storm Harvey. Storm Harvey that hit the eastern seaboard of the U.S. Now, hurricanes are going to occur. Hurricanes are a natural distribution of energy system for the planet. You build up energy, it moves here and distributes the energy. But it's the intensity of the storm that can be related to more severe hurricane. Warmer oceans. Warm water is what fuels hurricanes. They're called typhoons and cyclones in the Pacific, but it is a storm. Warmer temperatures fuel stronger hurricane. That's why oftentimes you hear that when a hurricane, as it moves further north up along the eastern seaboard, it peters out. It loses its energy because the water is cooler. It can't draw energy, moisture energy from the surface. You have hotter water temperatures, as I just described to you, having more increased temperatures. There's more energy in there, and it'll be more devastating. Okay. Not only, excuse me, did I say Storm Harvey? That was Texas. I meant to say Storm Sandy. Excuse me. Storm Sandy that pummeled the East Coast. Harvey hit Texas. And that was a storm that just dropped an ocean worth of water in Texas there. Very devastating there. So the thing is it's not so much that, climate change causes hurricanes. No. Hurricanes is a natural event. This climate change due to global warming makes such storms more severe, more devastating. Okay? And you get these, also I should mention, along with increased sea levels, you have increased flooding. Okay? Could be from places like Bangladesh, Holland, many places in Europe or coastal Africa, coastal Scandinavia, South America, etc. Okay. So, yes, climate change does not create hurricanes, but allows them to be much stronger, more devastating, transferring more energy. In fact, with Harvey and some of these storms of the last hurricane season, they actually created or talking of creating a new category for hurricane. Currently we have 5 categories. Such and such a hurricane's a Cat 3 storm or a Cat 4. Well, Harvey had sustained winds before it went over Texas, had sustained winds of 180, 182 miles per hour. So they're thinking of creating a Category 6 classification. That tells you something right there. Okay, that is all the time I have for this edition of Science Talk. I thank you for your time. I thank you for your patience and listening to me as I bring you these reports. Please go to patreon.com and support this work. Spread the word. Thank you.